xy squared is equal to 3k. Oh, can I change that, guys? Doesn't it really mean k is equal to, am I fading with my glass? Does that mean k is equal to stuff? Now, equating my k's doesn't that mean this?
Are you just substituting?
Yeah, because they're both equal to k, so I'm just substituting in, nothing more. Why are you guys looking at this so strangely? Because,
One equation, two variables.
yeah, it's awful looking. It's okay that it's one equation, two variables, because it's really a path, but it talks about the path I would move along. I think my example is very complex. I think it's too sophisticated. I didn't do anything wrong, but because the relationship is so strong in terms of cubic polynomial, it's kind of hard to see what's going on. So let me change it. Let me change it to question number 2. This service. Because I think you and I can picture what the heck this thing really looks like. I said, I think you and I can picture what this thing really looks like.
Does
Yes.
it
Do you
look
have
like
to
an elliptic
solve
parabola?
for one of those variables in terms of the other two?
No, I'm just simply saying all the points x comma y satisfying that equation, or the points that have the quality,
Right,
that the greatest is in the direction of 1 comma 3.
but, I mean, you would put it in terms of y or x if you were to put it into like a computer.
Actually, I can't solve explicitly for y in that equation.
Okay,
I can only solve implicitly. I can only state the relationship implicitly.
Okay.
And I have.
okay.
You guys, let me change the question, because you and I can visualize this,
Elliptical paraboloid?
yeah, actually, in this case, it's circular paraboloid.
Circular paraboloid?
I think it looks like this. And at the x-axis, if I plant my feet at the point, excuse me, I misspoke. If I look in the direction of 1 comma 3, what points in the xy coordinate plane tell me that the corresponding values are going to give me the greatest descent in that direction? I think I can answer this question the same way. I just think this relationship is so complicated. Let me go ahead and redo my work with an easier example. So, same question here. I think here too, the gradient for f, evaluated, I don't know where yet, has got to be some multiple of this vector 1 comma 3. It's just I'm making up another example where I think our answer is going to be more simplistic. So you guys take over and compute the gradient vector. What do you get? 2x comma 2y. And if these vectors really are the same, I do insist that equating components gives me these two relationships, suggesting that x is equal to 2x, or k is equal to 2x, and k is equal to 2/3 y as well. And in equating my k values, doesn't that merely mean that 2x is equal to 2/3 y? Or shall I say, y is equal to 3x? So Linda, you remember you asked me how would I solve for y in this equation? It's too complex, but look at this equation. I can.
Right.
What does this really say in English? Well, look at my picture. It says if you draw the line y equals 3x, which kind of looks like this, in red, and this line is in the xy coordinate plane. Okay, not in red. How about blue? Here's my line y equals, is it 3x? In the xy coordinate plane. If you walk on this line and look at any point on the actual surface, at those points, there's infinitely many, I will have it going in the direction of 1 comma 3 being the direction of greatest descent.
But given that this is an elliptic paraboloid, and a and b are equal to 0, the direction of greatest descent could be any direction, as long as you're heading out away from the origin.
Now, wait. I'm talking about specifically those points in the surface that have the quality that when you look in the direction 1, 3, that is the direction of greatest descent.
Okay.
So it's a very backwards type question if you're only saying it that way.
So because we're dealing with a circle, it would land on that line that
Yeah.
it's always,
Well, I think even if I change it to an elliptical paraboloid, I just made this up because I wanted something more simplistic. But even elliptical paraboloid, my answer's not going to change. It'll be a nice clean line.
yeah, but if you had something more complicated, like it oscillates in and out or
And that's exactly why, because of what Linda asked, I was nervous about my example number one. Because to answer this question with example number one, I said, oh, you need to move in a direction on some curve in two space, and yes, y coordinate plane. What curve? Well, the curve described by this implicit equation. It's a complicated curve. And so now I'm creating an easier example, so you can clearly see what that curve looks like. Oh, it's in blue. Actually, it's a simple one. It's just a line.
Okay, I'm not seeing it yet. So the
Oh, no, really?
No, so the 1-3 direction,
Yes.
and we figured out that line. So on the curve, show me where we're talking about the ascent and descent and why that's greater.
Do you guys think I can do this? Take a peek at the line y equals 3x. Create a vertical plane that's perpendicular to the sy coordinate plane, but cuts through the blue line. And now look at the intersection of that plane with that surface. Wouldn't that intersection kind of look like this? And so I think a slice through this surface, which is a paraboloid, I think the corresponding slice in this plane that slices through the blue line is going to be another parabola. And I think any point of that parabola that's on the surface will have the quality that if you look in that direction, you will be looking in the direction of greatest ascent. That's all I meant.
Is it a coincidence that when you do the y over x of that side, y over x, that side, that happens to be the equation of the line? Like you do 2y over x. That's y. That's
No
y over
coincidence
x.
whatsoever. It really does come back to the idea that that direction is going to be perpendicular to whatever tangent line you have. So it's no coincidence that they really have the same values.
Okay.
But I gotta confess, if that surface in 3 space is more complex, I think the relationship is going to be more complex like this example. I just got lucky here because I chose a nice, clean, simple circular parabola.
So couldn't you just do like y over x equals 3k over k, and then k's cancel out, and you have 3 equals, or y over x equals 3, and then just multiply the x over, and you get y.
Well, unfortunately, if it were an elliptical paraboloid, these coefficients would change. It would change that ratio. That's why I'm saying, Matthew, I got lucky because I chose a circular paraboloid. If you're an elliptical one, then it wouldn't be that quite straightforward.
You can't do it.
It would still be it would still be an easy equation of the line. I'm just saying these two coefficients would be the same. So the ratio of these two coefficients does not give you the slope of the line. That's all I'm suggesting.
Well, okay, I'll just ask my question. So with the whole direction of greatest ascent or ascent,
Yes.
being perpendicular to the tangent line, is that because of, well, I mean, we looked at it with this level first. Is that a result of the fact that they're all seen in terms of x and y, so they're all gonna?
Yes, I agree.
So how would that affect things with, functions that have discontinuities?
Ooh, tremendously. I gotta confess, I don't even want to get into the issue where I've got points of discontinuity. I only want to talk about smooth, I shouldn't say smooth. I want to talk about continuous surfaces. And I am restricting my attention to those kind of surfaces.
Can you do a counter example?
What do you
Like-
mean a counterexample?
Well, so at 1-3,
Yes. Whoa, back up for a minute. You said at 1-3, that's a vector.
I
not a
mean,
point.
excuse me, in the direction of 1-3, can you do a counter example?
Do you mean find another point on the surface, not on this parabola, for which to point
But it's in that direction, so showing that the ascent is a different.
is a different vector? Piece of cake.
No, I want that vector, but a different ascent with that vector.
That direction or a different?
Okay, you said the direction of greatest ascent.
Right. So you're saying pick a different point that looks in that direction that's not on that line.
So then, with what Catherine's saying, let me rephrase it, and tell me if I'm really looking at this the way you want me to. Plan myself at this point. In the SY coordinate plane. Look in the direction of, I've lost it, 1, 3, and show you that this direction is not the direction of greatest ascent when I look at the corresponding point on the surface.
I guess, yeah.
Okay. I'm sorry if I messed that up.
Yeah.
Then let's do it. I think I've already got the gradient vector. And can I just pick a point not on the line? How about in green? How about the point 4, 1?
No, that's not what I'm asking.
Oh.
Because
I
you're saying
apologize.
I just wanna see on the surface, different ascents, I guess.
That's what,
Yeah,
And that's what I'm gonna do.
okay.
I'm gonna go up to the point on the surface where x and y are 4 and 1 respectively. But I'm gonna show you the direction of greatest ascent is not that direction.
Right,
I'll prove to you that's the case. I will, at least at that particular point.
okay.
So let me do two things. Number one, let me go ahead and find what the direction of the derivative is in the direction of u-bar. At that point, I made up out of thin air 4, 1. When? Sorry, guys, I'll stop writing in green. I can't read this. When u-bar is going to be nothing more than 1, 3. It's just, if you guys don't mind, I'm going to unitize or normalize the vector. Would that be a 1 over root 10? 3 over root 10? I think the direction of the derivative, if I is the following, merely my 2x, 2y, dotted with 1 root 10, 3 root 10. When? X is equal to 4 and y is 1. Which I think, numerically speaking, is nothing more than this. Ay, ay, ay. Is that a 8? 1 dotted with this.
8, 2, 8, 2.
Oh, is it 2? Thank you very much. Which I think amounts to this. Is it a 16 over root 10? Oh, so I can't add. So 8 plus 6 is 16. Thank you very much. That's how fast the z values are changing for 1 unit change in the direction of that green vector over there. However, if I were to compute the gradient vector for my function f at specifically the point 4, 1, let's see what we get. I think I get nothing more than, is that an 8, 2? And I think the magnitude of del f eval of 4, 1 is nothing more than, yeah. Can you guys help me with this one? Is that a, oh yeah. 64 plus 4? Maddie?
this is probably a ridiculous question, but what is du? Like, what is it?
It's the directional derivative. It's the rate of change of my z values looking in the direction of u-bar. Everything you and I discussed last time in class. So consider this tabletop, the xy coordinate. Here's the surface. Plant my feet at a point A, B in the xy coordinate plane. Go straight up to the surface, and I think look in the direction of u-bar, unit vector down here, emanating from that
D
point.
is the vector? D in that direction?
Say
Is that what du is? U is being the direction and D just being the vector?
No, so let me back up. At that point, go up to the surface. I think v sub u-bar is nothing more than the change in the z values going in the direction of u-bar. It's how fast my z values are changing. It's just like f prime of n, just in a higher dimensional space.
Oh.
And unlike partial derivatives, I'm not necessarily planting my feet at a point A, B and looking in the x direction only or looking in the y direction. I'm not looking in any direction. I just wanted you to make sure that it's a unit vector so I can see the corresponding change in z values for an increase of 1 in the xy coordinate plane.
So, I'm trying to visualize this, but, so the directional derivative is like, let's say like the y equals x, y equals 3x, that, let's say there's like a plane going through that thing, and I forgot what's it called, the elliptic parabola, or the circular paraboloid thing is going out forever, and that line's going out forever, and that, like, you take the tangent line to the shape as it's going, like, as that line's going out forever, like that. You see what I'm trying
But
to
I
say?
think that line has nothing to do with the directional derivative in general. I think the directional derivative at a certain point A, B in a certain direction of u-bar is simply describing at a certain point on the surface how fast your z values are changing looking in the direction of u-bar. That's way down there in the xy coordinate plane.
At that specific point.
Yeah, well, at the specific A comma B in the XY coordinate plane, you're right.
But I don't know.
So you could give us a direction and ask us to find an equation that gives every point where that's the greatest descent.
Thank you.
Or. you
Well, that's
give
the
us-
direction of greatest descent, yes.
A shape. Or you give us a shape and then a point and ask us to find what is the greatest descent at that point.
Yes, certainly I can ask those two questions. And I confess with my,
That's both ways, right?
yes.
At the same time.
And I think with my first question, it's just that curve in the XY coordinate plane was much more complex than a simple blue beast. But I have not answered your question yet.
No.
So Linda, check this out. Can I be sloppy? I want to pull out a calculator. This is kind of like close to 3. Well, root 10 is close to root 9, which is close to 3.
4.427.
If you insist. Your darn technology. Say it again.
4.427.
What about this?
8.246.
Linda, I did it. I think at that point, 4, 1. Look in the direction of the vector 1, 3. There's how fast my z values are changing. It's just that I think looking in, oh, look this direction right here. I think actually the ascent is going to be greater. So I think that answers your question the way I interpreted it.
And you made a 8.2?
Well, 8, 2 is nothing more than gradient vector divided 4, 1.
Oh.
And here's the gradient vector right
That's
here.
what it is.
Can I draw you from what I'm trying to tell you?
Yes, you can, please.
So, is the directional derivative like this tangent line that's like that, as it's like moving, and it's like these correspond to this line right here?
But a directional derivative is not a tangent line, it's a number.
Okay.
So you can think of it as a slope of a tangent line.
Okay.
So when you draw those tangent lines to the surface, we're really talking about the directional derivative being the slope of those tangent lines.
Okay, but the slope isn't, but it's like, at this point though, it's not as it's moving along the curve.
True, at a single point, I agree.
Okay, then what about like when it's moving along the curve then? Like, how do you get like that derivative, I guess? I don't know what I'm trying to say.
Is this easy? You're simply going to compute the directional derivative to be nothing more than dot product of the gradient vector with whichever direction you want to walk in. That's your computational tool, your math object, to compute the directional derivative. Simply gives you rate of change in z values in the direction of each one.
I was just gonna ask, kind of related to that question, what is the gradient vector, just visually speaking?
What a good question. There's a couple different ways I can answer that question. Number 1, it's a vector. Although I confess it's not constant, is it? Depends on the evaluation effect, depends what x and y is. But here's something else I can say. I lost my good black pen. Can that be treated as a slope of a tangent line?
Yes.
Yeah, at some value of x. Is this the same as this?
No. Hmm.
See, I think the answer is yes. I think I come up with dy dx by differentially operating on my y. And so I sometimes think of this as a differential operator. And so I think for the same reason, I can think of the del itself as an operator. It's just instead of operating on functions, it's operating on vectors. Because it takes some vector up here and differentiates its components with respect to x, y, and maybe even z in higher dimensional space. So that's why I stalled and said I can answer your question a couple different ways. Yeah, it's just direct differentiation. I get a vector, done. But this symbol right here is an operator on a vector valued function, just like d over dx was an operator of functions back in math 30. Same idea.
So del F is like ddx in this equation.
No, say del is like d over dx.
Del.
You said del f.
Yeah, yeah.
Because to me, del f is the actual vector, not an operator. You guys, let me shake you up, because of all these questions. Let me shake you up to see if you really understand what's going on. Along this line, in the xy coordinate plane, I want a yes or no answer. Is it looking in this direction for every corresponding point on the surface that I get the direction of greatest ascent?
Yes.
No, because it's only directly on top of that line where that direction will give you the greatest descent.
Didn't you say along that line?
Or that's what I just said.
For this particular,
Yeah, it's just, that's what I said. I said, along this line, going to the surface, I think any point on the surface corresponding to this line in blue are going to give me the points for which, when I look in that direction, I get the direction of greatest ascent.
yes, that's correct. Or descent if you're on the negative side of the origin, I guess.
Oh, see, I think it's irrelevant. Even if you're on the back side, it's still going to be looking in this direction. I said looking in that direction. It could be going backwards. So it's irrelevant.
I have a weird question, but if you took the directional derivative of every point along the elliptic paraboloid along the y equals 3x, that would give you a plane, right?
Well, I'm just saying this red curve is a cross-sectional slice of a plane sliced into my surface that's passed through the blue line and perpendicular to the SY coordinate plane.
Now, because this is a symmetric surface,
Mm-hmm.
are we gonna have this, no matter which direction we point, we're gonna have the same V value?
Well, see, that was my next question. That's why when I said I want to shake you guys up, you never let me finish my questions. So go back. So do you agree that along this line, look at the corresponding curve of the surface, every single point has a quality that when I look in this direction, I get the direction of greatest ascent? Good, the answer is yes. Now, come back to all these points in the red curve, which is simply a portion of the surface. Is it true that when you look in this direction, the value of the directional derivative is the same? No, I don't think it is. I think it's a different value. Of course it's a different value, because I've got a factor in which I've got that non-constant vector value function. And so I think it does clearly depend on what x and y are. It still may be the case that any point on the red curve in the direction of 3, 1, or excuse me, 1, 3, it is the direction of greatest ascent, but the value of the ascent for the z's is not going to be the same at any point on that red curve. Are you there? Okay, good. I'm happy.
I have a question.
Yes.
When you talked about the level curves
Yes.
and tangent lines and then greatest descent would be perpendicular, I'm having trouble seeing why.
This is 3-6, right?
What's that?
That's 3 space?
Well, I'm just looking at level curves that are two-dimensional. It's just that when you rise them off the inkward, they become three-dimensional curves. So if this is a level curve, and here's a level curve, and I've got a particular point, say A, comma B, I maintain the directional derivative is going to be pointing in this direction, merely perpendicular to where the tangent line is to my curve at that particular point. They're going to be orthogonal. If this is a level curve for some surface, if this is going to be a level curve for the surface described this way, I think I'm simply suggesting that this particular level curve has a constant value for z, say for example 3. In other words, along this curve, all the z values in my surface are positive 3. This is sort of like a cross-sectional slice to my surface in 3 space when z is equal to 3.
So is that what the directional derivative is? It gives you the z value at that specific point? Or that specific
No, quite the contrary. The directional derivative does not give you a z value. That's given by this particular equation. The directional derivative simply tells me how fast the z values are changing at that point on the surface.
I'm just having a hard time visualizing it.
Well, do this then. Here's my surface. And let's talk about this point right here.
Okay.
Now, the directional derivative will be telling me how fast my z values are changing. Well, actually, what direction?
well, whichever direction.
Whichever direction, darn well, please describe my u bar. So if u bar is pointing in this direction, then my z values are changing slightly higher. They're increasing slightly with this particular surface. But what if I'm at this point and u bar is going in that direction? Is it not the case that z values are decreasing?
Yeah.
I'm sorry for this lousy problem. Did you get the idea?
Yeah.
And so you can't say the direction of the z values is how fast the z values are changing, and it depends on what direction you're pointing in. And it really depends on what point you're looking at in the xy coordinate plane.
It's just the slope.
It is a slope back, that's all it is.
Okay.
I understand all that, I just don't understand when you do this thing, what is that? Like, I don't understand what this is, so this is a cross-sectional slice of something in.
Well, if I asked you to consider this surface.
So like this outer line might be when z equals 4, is that what?
Yeah, so let me draw my x-axis, let me draw my y-axis, let me draw my z-axis. I'm just simply going back to how you and I described surfaces a few sections ago. Watch. I'll unitize. Now, if I took a cross-section slice to the surface when z is equal to 0, what do I get? I agree, and it's at the origin in the xy coordinate plane. But if I take a peek at the cross-sectional slice when z is equal to 1, what's the corresponding image with this equation right here?
It's gonna be an ellipse.
Yeah, I agree. It'll be some kind of ellipse. And what's going to happen with the cross-sectional slice of the surface when z is equal to 2?
Bigger.
Same thing as ellipse. And when z is equal to 3?
Slightly bigger ellipse.
Yeah, slightly bigger ellipse, but they just all have the same distance between them, right?
As far as we know, yeah.
I think the answer is no. I think the answer is no because I don't think the outer surface is linear.
Oh.
Because the curvature, I think as in this case, z increases by every integer, I think this concentric ellipses are getting closer and closer together.
Oh, like
Sorry for the poor picture, you guys.
like the contour lines on a hill on a map.
Very much like the contour lines, that those are nothing more than level curves. Do you guys agree?
So it's the same function at different times, or different z's, or whatever.
Yeah, I agree. It's just that with the picture I have on the board over here, it's a more complex surface than I have over here. It was just easier to talk about those cross-sectional slices. What do you think so far?
Okay, so then you're saying at any point on the first time, the perpendicular line is going to be the greatest ascent?
It is going to be the case that the angle, Matthew,
Oh, thanks for her question for that.
the angle between these two is going to be a right angle.
And what's the significance of that? That's the greatest ascent? Or why is the tangent, why is the perpendicular to the tangent line at that point? What is it again?
Okay, how about this? You guys here remember this? Yes? Yeah, it's our working definition. Maybe a definition, it's our working formula for computing directional derivatives. What about this?
Yeah, that's
Use
different.
Magnitude. Piece of cake. What is this equal to 0?
When is it equal to 0?
Well, okay, if it is equal to 0, what would the angle have to be?
270.
Have to be 90 degrees. But if it's equal to 90 degrees, doesn't that mean these two vectors are perpendicular? And so perpendicularity occurs when actually I'm traveling along the curve. Perpendicularity occurs when I'm traveling on the level surface because look at the directional derivative. I mean, it's not changing when I'm moving on that particular curve. The z values aren't changing at all. So I think they have to be meeting each other at a right angle because the dot product's equal to 0. Do you see it, Catherine? So it has to be true.
So theoretically, you could ask us a question on a test like, get the equation of the plane, that slicing, that thing at the point there, and then we would have to do like the cross product in that plane.
Well, now, when you look at the cross product, you're changing the name of the game because now you're going perpendicular to what I have for this collection of level curves.
Yeah, but if you want the equation of the plane that's slicing that level curve, then you have to do the cross product of that vector and that vector, right?
I suppose, I just don't know why you'd want to take a peek at that particular plane slicing through the surface. I think it would be more interesting is look at the plane slicing this way. But we already know all the z values. How about change the name of the game? How about, wow, third example. I won't finish my example. Jeepers, what about this? Before you guys take off.
You could make it a quiz.
No. It's a surface of free space. But I think, if I think of the output as some function in x, y, and z, I can just as easily talk about the gradient vector for f, because here it's just gonna be nothing more than the partial of f respect to x, partial of x respect to y, partial of f respect to z as individual components. And I think the only difference is now I'm looking at level curves, oh shoot, I'm not, they're level surfaces for a four-dimensional object, but I still have the same game. What direction do I point? To move from one level surface most rapidly to the next, it would be in the direction of the gradient vector. By the way, I don't have to stop. I can keep going in a higher dimensional space. It's just more difficult for you and I to visualize the corresponding level surfaces.
Wait, wouldn't it be a level volume along a four-dimensional object?
Well, it wouldn't be a volume because we're talking about level or cross-sectional slices, which is not a number. It's an actual shape. And when you say volume, that's a quantity describing something.
Okay.
It'd be like a gradient volume then.
Gradient volume. I suppose you can consider a function that gives you volume in terms of various different variables. I can maybe make it work better.